everybody have your periodic table out? Okay. Okay. This chapter is chemical periodicity, which is the same thing as just looking at more trends of the periodic table. Okay. We're going to look at the atomic radius, which is also the size of an atom, and how that trend is portrayed in our periodic table. We're going to look at an ionic radius, meaning what's the difference between a neutral atom and the size of it if it is an ion, so an anion or a cation. Okay, we're going to talk about electronegativity, which is one of my favorite terms, and I use it throughout all the chemistry classes that I teach, so we'll talk about it, and then we'll talk even more about it through the week. Okay, and then the fifth one is ionization energy, and so we'll talk about what that means and the trend of the periodic table. Okay, so this is a review, quite a few of these here. All right. So if we look at all of our noble gases and we write out their configurations, we see that they all have a full shell, right? They're P6, and then of course helium's just a 1s2 because it's up there at the very top. Okay, so they all have similar electronic structures. Okay, even though, you know, krypton has more electrons in there than argon, okay, they're still very similar because they still have their p orbitals are full. Oops. Okay, we've already mentioned this as well, so we're a little ahead of the game here, but our representative elements are the ones that follow the trends more closely. Okay, these are the ones we're going to look at the most. Okay, these all have their electrons, their last electron in the S or in the P. So here's 1, 2, and we skip over our transition metals, 3, 4, 5, 6, 7, 8. So there's 8 groups that we consider representative elements. Okay, and they have fairly regular variations in their properties, and like I said, they follow trends more ideally than our transition metals. Okay, our D transition metals are the B groups. And they have D electrons, so that's where their configuration ends. And they have very small variations from row to row. And like I said, there's a lot of exceptions in this area. So some of these metals, especially ones that are very useful to us, there's, you know, a whole, you know, semester you can talk about just one of these elements and the way that it reacts. Okay. And we don't talk about a lot of our F transition metals. Uranium's probably the most common or one that you've heard of the most, but all of these are not naturally occurring. They are radioactive. Anything past bismuth is radioactive, so we talk about these in Chem 112. But some of these don't even have a lifespan of more than a few seconds, so we don't really even get to talk about them. They're not, as of now, as useful to us as our group A elements. Okay. Okay, the atomic radii, or the radius of an atom, describes the relative size of atoms. Okay, so you just want to think about it. How big or how small is the atom? Okay, this is going to increase as you go down a column. Okay. So that makes sense because if you think about it, every time that we move down to another period, what's happening to our atom and its orbitals? We're getting more and more energy levels, right? Okay, so that makes sense. We have more electrons and we're getting more and more energy levels around the nucleus. So as we go down the periodic table, size increases. Okay. However, when we go across a row, okay, so if we move from left to right, okay, the atomic radius decreases. Okay, so this is kind of not a trap for students, but sometimes it's confusing. Okay, so as you move down, it gets larger, but as you move from left to right, the atom gets smaller. Okay, why do you think this is? Okay, most people look at the periodic table and think, well, you know, fluorine has more electrons than nitrogen or oxygen. So why is it smaller than nitrogen or oxygen. Okay, so it's contrary to what you would think. Anybody have any idea? Okay, to the nucleus maybe? Is that what you're getting at? Okay, yes, it does. Okay. Yep. Okay, he's right on track. Okay, so as we move from left to right, we have more electrons, right? So if you look at fluorine, it's got more electrons than nitrogen, oxygen. Okay, so the more electrons, they are negatively charged, right? Okay, what's the charge of our nucleus? Positive. Okay, so what happens when you have negative and positive? What do they do? Attract, and essentially almost shrinks the atom because they have such a strong force holding them together like a magnet. Okay, so as you move left to right, you get that kind of very strong attraction. It's called electrostatic attraction or potential. Okay, and it makes the atom actually smaller. Okay, it's not, as you can see here, as you move down, you get a lot bigger. Okay, so that's kind of has more of an effect as you're going down the periodic table, the more energy levels that there are. Okay, but you do see this decrease in the size. It's not quite as dramatic, okay, but it's a pretty big difference. So even up here, so there's fluorine. It's a smaller atom, so it's much smaller than your lithium atom. Okay, so let me go back here real quick. When we're dealing with trends, students can look at this in two different ways. You can just remember exactly what I just said. As you move down, it gets bigger. As you move across, it gets smaller. Or you can also try to remember that down furthest left, cesium is the largest atom. Okay, there's francium below it, but it's not naturally occurring. Okay, and so if you think about that and if you remember that, then if you move this way or you move this way, you're going to get smaller. Okay? Or you can think about it as, up here with neon, fluorine, those are the smallest. So if you move away or you move down or across, then you're going to get bigger. Okay, so you don't have to, if you want to think of it that way, you can. Okay, so I already have the, already has the answer there on accident. Okay, if we arrange these elements based on their atomic radii from smallest to largest, so be sure you pay attention to your homework and to in the exam to put it in order from smallest to largest or largest to smallest depending on what you're asked. Okay, so pay attention to that. Okay, so if we're going from smallest to largest, and you look at your periodic table, oxygen is the furthest to the right in the upper right corner, right? Okay, and so as you move away, then comes sulfur, okay, then comes the next two here. Okay, so does everybody agree with that if you look at your periodic table? Okay, do these. You've got all nonmetals here. Smallest to largest. Okay, so what's the smallest radius here? Chlorine, because it's the furthest to the upper right. All right, what comes next? sulfur, and then all right, does that look right? I think this is the last one, so do this one. And these are a little bit more spread out. So range from smallest to largest. Okay, smallest would be, all right, next, then arsenic, and then, all right, easy enough. Okay, if you're comparing a neutral atom to an ion, there is a trend, okay? And it's pretty easy to remember, even though electrons are very small and we consider them pretty much negligible mass. But if you have a cation, okay, that means that this is going to be a metal, right? Because metals lose electrons, okay? And a cation means that it has lost electrons compared to that of its neutral atom, okay? And if you lose electrons, so think about you're losing something, you're losing electrons from your atom, then the ion, the cation, is going to be smaller compared to that of the neutral atom. Okay, so if we look here, so here's the atomic radius. This is angstroms, that's just the unit for the length. And it has 1.52 as its radius, and then here's its ion form. Okay, lithium's in group 1, so that makes sense, right? It forms a +1 charge. It loses 1 electron. Okay, and then its radius is now 0.90. Okay, and so its radius is smaller compared to that of the neutral form. Same for beryllium here. It was 1.12. It's in group 2, so it loses 2 electrons. Okay, and the radius would be 0.59. Okay, so the cation is smaller than the neutral form. Okay, if you have an anion, what do you think is going to be the trend? Yeah, it's going to be the opposite, right? So if you gain electrons, you're gaining, even though it's a negligible mass, you're still gaining a particle to the atom, and so it's going to be larger. So anions, negative ions, are always larger than their neutral atoms. Okay, so you want to look at it here in these columns here. So 0.75 is the radius neutral. Nitrogen gains 3 electrons. Okay, why does it gain 3? If you look at the periodic table, it's 3 electrons away from being like neon, right? Okay, so it's N3 minus, and now its radius went up quite a bit there to 1.71. Okay, oxygen, it gains 2, so its radius went up as well. And then fluorine gains 1, and then there's the radius of fluorine as it's gained an electron. Okay, so the radius gets larger as it gains electrons. On the first exam, there will be, a couple questions about electronegativity. We won't well, we'll see how far we get. Take that back. And maybe more than that. So we'll see how far we get before the first exam. But this will be repeatedly on exams. So we'll build on electronegativity this term as we go on. So this week we'll just kind of start talking about it. We'll pick up and talk about it more on Wednesday, and then we'll continue to talk about it. So it's very important. I tell my students, I'm not a big definition person. I don't expect you to recite every definition exactly back to me, but this is one that I would know. Okay, so this is one that we'll see over and over, and you definitely want to know it. But basically, what electronegativity is, it's the measure of an atom's ability to attract electrons to itself, okay, in a bond. Okay, and so we haven't talked a lot about bonds yet. We're going to get to that next. Okay, but it's the ability to attract electrons, or the tendency of an atom to attract electrons to itself. Okay, so we have a trend here as well, just like we've had a trend for atomic radius and for cations and anions. Okay, how I usually remember is that fluorine is the most electronegative element. Okay, so you're up to the far right. Okay, your noble gases, they don't really attract electrons, so they're not included here because they're stable, right? They don't really need any more electrons. Okay, it makes sense that fluorine would be the most electronegative because it wants one electron, right? So it wants to attract an electron to itself. Okay, cesium and francium, so down here, okay, these are opposite trends. So fluorine's the most electronegative, cesium and francium are the least electronegative. Okay, which makes sense because metals, do they want to attract electrons to themselves? No, right? They want to lose electrons. Yes. Okay. It's not necessarily always reactivity. It's more of how, in a bond, how they attract to each other. So once they're already bonded. So yeah, it's not necessarily reactivity. Okay, so the trend, it increases from left to right. Okay, so that makes sense because fluorine's our most electronegative, and it decreases from top to bottom. So basically, if you remember that fluorine's the most electronegative element, that if you move away or you move down from it, it's going to be less electronegative. Here's some values. So there are values given to elements. You don't have to memorize these because we just want to know the trend. But I do want you to notice something. So if we look up here, fluorine, that's one I have memorized, but it has an electronegativity value of 4. Okay. If we look next to it, oxygen, 3.5. Okay, so these are just our values. But if you look over here, cesium is 0.8. Okay? So there's a large difference between cesium and fluorine, right? Okay, and you'll see this trend throughout, and you'll see where I'm getting to here in a little while. But a metal and a non-metal, there's a big difference in electronegativity. Okay, we consider 1 versus 3, anything more than like 1.8 is considered to be a big difference. Okay. So if we look at the difference, what's the difference in electronegativity between chlorine and calcium? What's the difference? 2. Okay, that's a big difference. We consider that to be on a 2 doesn't really sound like a large, but with electronegativity, that's a large difference. Okay, anything above really 1.8-ish is about, we consider that large. Okay, so if we arrange these from lowest to highest electronegativity. So if you look at your periodic table, see if you agree with this trend here, this setup. Okay, the furthest away from fluorine is going to be the first element. Okay, so if you follow across, okay, that looks good to me. They're all in the same period there. So the one that's the furthest away from fluorine or the furthest to the left is going to be the lowest. Everybody agree? do these? Okay, we're over in the metals. So barium is further down. Okay, so it's going to be the lowest electronegativity value. Then calcium. Then everybody get this? Is that the only one I have for there? Yes. It increases as you go from left to right. Okay, the last trend is sort of the opposite of electronegativity. Okay, it's called the ionization energy. Okay, and we have what's called first ionization energy and second ionization energy. Okay, the first ionization energy, so IE1, that's the main one that we're going to be looking at. So I'm just going to mention this one and show you what it is. But this is the amount of energy required to remove the most loosely bound electron, okay, which means that's going to be your valence electron, right? That's more loosely bound, that's in the valence shell. Okay, and it's all this is done in the gas phase, and it forms a 1+ ion. Okay, so you hit this atom with a certain amount of energy, okay, and this is called its ionization energy. And one electron is lost, okay, and then it forms the ion plus, okay. The second ionization energy is just how much energy is required to move a second electron. So you would take that ion that you form that +1, and now you'd hit it with some more energy, and you'd form an ion with a 2+ charge, okay. So we know that metals, they want to lose electrons, right? Okay, so they have lower ionization energies than nonmetals. Okay, this makes sense because for a metal, it's not going to take as much energy to lose that electron, right? Because that's what it wants to do anyways. It wants to be like the nearest noble gas. Okay, so our trend here looks like this. Okay. A few points here. So it always takes more energy to remove the second electrons. That's that first point. It always takes more energy to remove the second electron versus the first. Okay, but we're just going to look at the first ionization energy. Okay, it increases as you move from 1A to 8A elements. Okay, so the energy increases as you move from left to right. Okay, that makes sense, right? It's going to take more energy for fluorine to lose an electron, right? Because fluorine wants to do what? It wants to gain. So it doesn't want to lose, it wants to gain. So it's going to take a lot more energy for you to take a fluorine atom and hit it with a lot more energy for it to remove an electron because it's electronegative. It doesn't want to lose an electron. Okay, and then it is going to decrease. Okay, the energy that it takes to remove an electron is going to decrease as you move down. Okay, so here your lowest ionization energy is going to be, cesium, francium, your metals that are the farthest down on the periodic table. Okay, so you can remember it either way. Here's your highest energy, and then here's lowest energy, ionization energy. So it's just the energy that it takes to remove an electron. So it's going to take less energy to remove an electron from a metal because it wants to lose an electron versus a non-metal that wants to gain. It doesn't want to lose. So arrange these in their first ionization energy, so the first electron to be removed, okay, from lowest to highest. Okay, lowest meaning you're going to be, these all may be dealing with metals, yeah. Okay, but it's going to be the lowest energy that it takes. Lowest to highest. The lowest was the furthest to the bottom on the left. See if you got this. Everybody get this? So go to the furthest to the bottom, that's the lowest, and then move up. Okay, there's a few of these, so arrange these from lowest to highest energy. And this time you've got some metals and some non-metals. Everybody get this? Okay, I think this is the last one. Arrange from lowest to highest. Lowest is going to be the only metal that's here. So beryllium, which makes sense. It would take less energy for it to remove an electron. And then borons here just moving this way. They're all in the same period there. Okay. So these trends are going to be carried on to chapter 7. So that's going to be the last chapter, I believe, that we'll get to before your exam. One of the main ones is the trend for electronegativity, okay, and knowing what electronegativity is. So we're about to talk more about it here in a minute, so you'll see why it's so important. Okay, so we ended chapter 4 with our electron configurations. Chapter 5 really was just parts of it, but it's just trends. So that's it for chapter 5 that you'll be tested on. Okay, chapter 7 is one of our most important chapters, really, of the semester. Chapter 7 is about bonding. Okay, so we're finally getting into, we've looked at configurations and diagrams and talked, some about valence electrons and how many electrons an atom wants to gain or lose. Okay, now we're going to see this in action where it actually makes bonds. Okay, so that's what chemistry, usually our goal is, and especially synthetic chemistry, is we want to make bonds. We want to make them efficiently, and we want to make them usually in a very time-efficient way as well. And depending on what our reaction is, here's aspirin. Okay, and so this is just kind of the molecular diagram there. Okay, but we want to make bonds and make them in the correct fashion in order to make things like aspirin or other pharmaceuticals or whatever it might be. Okay, so here's all the points for this chapter. We're going to look at Lewis dot formulas. These are pretty simple little representations of our valence electrons. Then we're going to talk about our two types of bonding. There's ionic bonding and there's covalent bonding. And this will also bring in to play electronegativity, okay, because how things bond depends on their electronegativity that we just talked about. And then we're going to write Lewis formulas. We won't get to this today. And this is, I have a nice little pattern that I like to use and teach. We'll probably spend the majority of a class doing these, so it usually takes a little bit of time to learn these. Okay, and so 5 and 6 we won't get to today. Okay, so what is a bond? So use that word quite a bit. Okay, and we also call it a chemical bond. Okay, these are attractive forces that keep atoms together. Okay, there's two different types of attractive forces, but all in all, they are attractive forces that hold atoms together. Okay, the electrons that are involved in holding atoms together are the valence electrons. So we mentioned this earlier, that valence are the most important electrons, they're the most accessible, and they are reactive, okay, meaning that they are the ones that form the bonds. And this is actually a structure of, this is a anti-tumor agent that I made a few years ago. And as you can see, it's got all types of atoms here. So each of these creases, so you wouldn't know this, but these are carbons. Okay, we've got oxygens. Okay, this we won't talk about until you take organic, what these are here. Okay, but all kinds of shapes. Here we have a double bond. Okay, here we have a double bond to oxygen. Okay, so it takes all sorts of reactions and attractive forces here to hold this molecule together. All right, so our two types of chemical bonds. Okay. The first one that we're going to talk about is ionic bonding, and the second is covalent. Okay, we're going to talk mainly about ionic bonds today. Okay, ionic bonds are the result of electrostatic attractions. Okay, electrostatic means positive, negative charge attract, like our magnet that we've talked about. Okay, they are formed by the transfer of one or more electrons from one atom to another. Okay, so we're going to repeat this. Ionic bonds, okay, are electrostatic attractions, meaning positive, negative charge, are formed by the transfer of electrons. Okay, so we're going to look back at our orbital diagrams where we put our electrons in, and we're going to talk about how they transfer. Okay, a covalent bond results from the sharing of one or more electron pairs between two atoms. Okay, so the key here, ionic is transfer, covalent is sharing, okay, which we won't get to that one as much today. Okay, so to add to this, so if you're writing all this out, okay, ionic compounds are formed between elements with large electronegativity differences. Okay, so earlier I think we looked at fluorine and calcium, or chlorine and calcium, I can't remember. Okay, the further apart two atoms are on the periodic table, okay, the larger their difference in electronegativity. Okay, so we looked at that chart, so look at it again here. Okay, so if you look at bromine versus what's next to it, and you keep going, as you move all the way over here, the further apart two atoms are, the bigger the difference. Okay, we don't have to know the exact value. You don't have to memorize these values. You just need to know the further apart two atoms are, the bigger the electronegativity difference. Okay? So if we look at this, an ionic bond, what we just said, is formed between two atoms with a large difference. Okay, so typically, okay, for you guys, not always, there's always exceptions in chemistry, but for what you're going to be looking at in your purposes, an ionic bond is going to be formed between a metal and a non-metal. Okay, that goes along with that big difference, right? Because metals are over here, non-metals are over here, so they have a large difference in electronegativity. Okay. Covalent bonds are the opposite. So they're going to be formed between elements that have similar electronegativities. They don't necessarily have to be exact, but they have similar. Okay, and these are usually nonmetals. Okay, so if you look at so we think about our stair step over here. Okay, covalent bonds are going to be formed between atoms on this right-hand side, okay, which is only about 20% of our elements. Okay, so ionic, between a metal and a nonmetal, transfer of electrons. Okay, that's the first type of bonding. Covalent bonding is sharing of electrons between two or more nonmetals, okay, on the right of the stair step. Okay, before we start really showing bonding and how this works, and we're going to look at ionic first, where we transfer electrons. Okay, we want to be able to represent our valence electrons, and we do this in Lewis dot formulas. Okay, and all it is bookkeeping of your valence electrons, so it's pretty easy to do. Okay, and so why we're showing valence electrons once again is because these are the electrons that are involved in bonding. They are chemically important. So here's the Lewis dot structure. So I'm going to walk through these with you, but okay. Lithium is in group 1, right? So it has one valence electron. So you can place that valence electron around the symbol for it. Okay, you could place it on the other side if you wanted to. So this is not wrong if you did this. Okay, you could do this if you wanted to. You could do this. Okay, whoops. Okay, that's one big electron there. Okay, so none of those are wrong. You just have one electron around. Okay, when you write that element symbol, that means all of the other electrons, core electrons. Okay, so when you write lithium, that means all other electrons besides your valence, okay, and then you show the valence. Okay, if we were to look at magnesium, okay, the key here is, and we'll start seeing that here, is that you have 4 sides, okay, to your symbol that you fill in each side singly and then add to those sides if you need to. Okay, magnesium has 2 valence electrons, so we would place one here and here. Okay, this is not wrong either. You could do here and here, here and here. But the idea is that you place them singly around, because when you start to bond, okay, or you start to transfer, it's easier to see them if they're on different sides. Okay. Okay, where did I get the 2 electrons from? How did I know magnesium had 2 valence electrons? Group 2. All right, what about nitrogen? What group's it in? 5. It has 5 valence electrons. So what you're going to do is you're going to do 1, 2, 3, 4, 5. Okay. Once again, if you wanted to go the other way or start differently, so if you wanted to do, let's say you wanted to do 1, 2, 3, 4, 5. Okay, that is not wrong. Okay, that's just you went a different way. Okay, the idea is that you end up having one paired here with an electron and then single ones on the other side. Okay, and you'll start to here probably Wednesday, see why we're doing this more than right now. But okay, then fluorine, so it's got 7, it's in group 7. So 1, 2, 4, 5, 6, and 7. Yep. Yep, basically you can kind of think of them as in orbitals. So yeah, you're going to singly atom Hund's rule and then pair them up. But it also helps you when you start bonding, because you'll start drawing out, say this was ammonia, NH3, then you'd have a hydrogen coming off. It helps you set up for your drawing of molecules as well. All right, what about carbon? Has 4 valence electrons. Okay. All right, so is this right? No. What about this? How about this? All right. So we get the picture here. Good job. Okay, so the first type of bonding, ionic bonds, so that's what we're going to look at. Okay, these are going to have charge. We have an ion, okay, and an atom or a group of atoms. We're just going to look at single atoms today. Okay, you're going to have a positive cation, which is going to be your metal, okay, because your metal loses electrons and forms cations. And you're going to have a nonmetal that has a negative charge. Okay, the theory behind an ionic bond is that your positive and negative charge attract. Okay, but not only that, you transfer electrons. Okay, so if we think about, I think I'm going to show this in a second. If you think about lithium and fluorine, okay, so we'll put lithium over here. Okay, so what's its valence electrons? How many valence electrons does it have? It's in group 1. Okay, so it forms a what charge if it's stable? A +1, right? Okay, what about fluorine? It always wants to form a -1. Okay, so how could these two attract? How could they transfer electrons? Couldn't lithium donate its electron to fluorine and make it essentially happy, right? Make it have its full octet. Okay, so that's what we're going to see here. Okay, we're going to look at what we call monatomic ions, meaning it's just a single atom. Okay, and so notice here, there's our cations, that those charges there, the Na+, the Ca2+, the aluminum 3+, you know those charges based upon what we have talked about. Those aren't coincidence that those are the charges. We know that sodium always wants to lose 1 because it's in group 1 to be like the nearest noble gas. Okay, so these charges don't just come out of thin air. Same with our nonmetals. Oxygen wants to gain 2. That's why it forms a 2-. Okay, these charges are also known as the oxidation state of an ion. So we would say the oxidation state of Na is +1, or of sodium is +1. Okay. We won't look at these today, but polyatomic ions contain more than one atom. Okay, so this whole group of atoms bears a -1 charge, or this whole group, this is carbonate, bears a 2- charge. Okay, so we will use these soon, but not today. Okay. So an ionic bond, once again, so I know I've said this quite a bit, but it's formed by the attraction of a cation and an anion. So that magnetic kind of attraction there. Okay, and usually a metal and a nonmetal. Okay, and it forms solids. So ionic compounds are typically strong, rigid structures. Okay, because of that strong attraction of that positive and negative charge, okay, they form strong compounds. They form solids. Okay. Okay, NaCl is an example. So we'll look at more examples, but that's just table salt, right? Na has a +1, chlorine has a -1, so they attract. Okay, so we can take all sorts of metals and nonmetals for many of our representative groups. So we have group 1, 2, and 3 metals, and then 4, 5, 6, 7. We're not really going to use 8 because those are our noble gases, but we can mix and match those. Here is we have a group 1 metal, so we have our lithium here, and we have a group 7, a halogen, nonmetal. Okay? When you react lithium solid, that's kind of a silver color, and fluorine gas, you end up with a white solid, lithium fluoride. Okay, it has a melting point of 842 degrees. That's a pretty high melting point, okay, meaning that it is hard to break. It's a pretty rigid structure. Okay, so let's look at the electronics of this. So this is just like what you've been drawing, except I'm going from left to right. Okay, it wouldn't let me go up and stack. Okay, so if we look here, we're going to make these look a little bit better here. So we know we have, these are our 2p orbitals. Okay. Lithium has 1 valence electron, so we know that's what makes it form lithium plus 1. Okay, and then we have 5 electrons here in our p orbital. We have 7 total in the valence. Okay, so what happens is we get a transfer. So I mentioned that term earlier. We get a transfer of electrons. So lithium donates an electron to fluorine. Okay, so these are just our orbital diagrams that we've drawn, and now we can see from that that lithium wants to lose an electron, fluorine wants to gain. Okay. When lithium loses an electron, it forms this plus 1, and it has the same configuration as helium. Okay? And what's the point of it all? The point is for us to get configurations like that of the what? Nearest noble gas, because they are stable, right? They have a full octet. Are we running over time? Okay. I see all these people running around out there. So, okay. All right. And then when fluorine gains an electron, so just imagine these are 3 lines here. Okay. Now it is fluoride with a negative charge, and now it is happy. It is stable, and it has a configuration like neon. Okay, you can also look at it this way. So the Lewis dot, go back to our Lewis dot structures. So we have lithium with that 1 electron there, and we just show how it is transferred to the fluorine. Okay, it's missing 1, and then now it has 1. Okay. You also see this written, so lithium plus and F minus. You have a plus 1 and a minus 1, but you'll see it written as neutral because we consider that plus and that minus, plus 1 minus 1 equals 0, right? Okay, so you will also see it written as this. Okay, and I've used these terms quite a bit. So lithium ion has 2 electrons and has the same electronic configuration as helium. So the whole point was for it to be isoelectronic with helium, and then for fluorine, it becomes fluoride, and it's isoelectronic with neon. Okay, so the whole idea here is that it has the same number of electrons as the nearest noble gas because it is stable. Okay, so now we can look at a different combination. Okay, we can take a 2A metal, okay, so look at your group 2, and a 7A nonmetal. So once again, we're going to look at a halogen, but this time we're going to look at a 2A. Okay. There are exceptions, but I wrote kind of those in, but we're going to look at what happens majority of the time, so we're not worried about exceptions here, but there are. Okay, if we take beryllium as a solid fluorine gas, we form BeF2, okay, beryllium fluoride. Okay, so if we look at our configuration here, Okay, so I'm going to have to draw some more into this here. Okay, so what group or how many valence electrons do we have for beryllium? We have 2. All right. How many electrons does fluorine want to gain? 1. Okay, so it can gain 1, but it cannot gain 2, right? Okay, so what do you think is going to happen here? Okay, if beryllium, it wants to give up 2. It's not going to give up just 1, okay, and be left with 1 in its shell. And fluorine wants to gain 1, not 2. Okay, so what do you think is going to happen? Exactly. You're going to end up with, so here's the p orbital of another fluorine here. So here's one fluorine atom. You're going to have another one. So that's why you end up with BeF2. Okay, it's not a coincidence that you have 2 fluorines. You need 2 fluorines for every 1 beryllium atom for them to bond in a way that gives them the more stable configuration. Okay? So you can look at this at the Lewis dot as well. Okay? So beryllium has 2 electrons. It's going to lose both of them. So it's going to need 2 fluorine atoms. So sometimes it's easier for students just to look at it as, you know, the valence electrons, the Lewis dot symbols. Okay. You end up with 2 fluorides and Be2+, but once again, you still have a 2+ charge on beryllium, and then you have that 2 out in front of the fluorine, okay, and you have a negative 2 charge there as well. So you'll see it written as neutral, as BeF2. Okay. So we can do this with different metals and different nonmetals and come up with our configuration. So what we just did was we came up with our, what we call an MX formula. Okay, M being the metal, and then X being the nonmetal. Okay, and so we just came up with, if we have a group 7 nonmetal and a group 2 metal, we get MX2, because we got BeF2. Okay, so we can do this for all of our metals and use different variations. And by using our orbital diagrams or the Lewis dot structures, we can see what our formulas would be. Okay, and so it's no coincidence to us that our formulas end up the way that they are. Okay, so here's a table. Okay, you don't have to memorize this because we just did 2 examples where you were able to derive these. These are examples here. You came up with an MX formula. Okay, so we'll do one more before we go here. Okay, if you look at let's look down here. Let's do this one right here. Okay. Okay, so if we look at sodium, okay, we know that it's going to have 1 valence electron. Okay, so in its 2s, I believe, or it's 3s. Okay, it's in group 1. Okay, and then if we look at oxygen, so it's valence electrons, I'm just showing the outermost shell. It's in the 2p. So this is oxygen. Okay. Oxygen wants to gain how many electrons? 2. Okay, but sodium only has what? 1. Okay, so we're going to need how many sodiums? Exactly. So that's why we get the formula Na2O, not NaO. Okay, and you'll start picking up on this even in lab and looking at compounds. Okay, it's always Na2O. We need 2 sodium atoms. Okay, we're going to have another one here. Okay, to react with oxygen so that both of them have their octet that's full. Okay, we call it an octet. Okay, and a stable configuration. Okay, so here's some more examples. So I suggest to you to go through and all these variations, so group 1A and 5A or 2A and 5A, okay, it's just the same thing, but to go through and do these on your own and be sure that you end up with these formulas. Because even here, there's an M3X2. We haven't looked at one that has a 3 atoms for every 2. Okay, so we can determine these by no coincidence by looking at our Lewis dot, our transfer of electrons, or by looking at our electron configuration diagrams and seeing how many electrons an atom wants to lose or gain. Okay, so we will pick up with this. So when you get here on Wednesday, you need to have done 1 through 4, and then I'll show you a shortcut. After you can do all those and know how you got the numbers, I'll show you a shortcut on how to do these as well. All right, I will see you in lab in a few minutes. So at 11 o'clock we have lab. So please be there on time and in proper attire, long pants, closed-toed shoes. I'll see you in a few minutes. Yep. Your first question was your first online homework. Yeah, it's due Wednesday. Yep. Yeah, if we don't get to it, what I'll do is you just won't have to finish that part if we don't get to it, and then it won't count against you on your grade. See y'all in a few minutes.